questions regarding homework or anything else? Okay.
Yeah, it was 3.26. The question was square wave current of source.
We're gonna do that. It shouldn't be that hard. Remember, they had a cosine series before. The guy put it in terms of a sine. It's a 90-degree station. And so once again, if you have a square wave, like so in the time domain, with a height a, I don't care what it is, this is tau and this is t, and it repeats itself. I'm just showing you what's the basic thing. We know that has a Fourier series representation, right? We know because it's periodic, correct? So the first thing I'm going to do is get C0. By the way, isn't the duty cycle 50%, right?
Mm-hmm.
All right, so that means tau is just t over 2, correct? Mm-hmm. And if that's the case, then C0, the average value, is just going to be equal A right there divided by 2. Do you all agree with that? Mm-hmm. All right, so I'm going to check that box. Now, after that, to get the actual Fourier series, we know, or the exponential series, the x of t is equal to C0 plus a summation, and I'm going to go from n equals minus infinity to infinity, but n unequal to 0 of C of n e to the j n omega naught t. The way I'm going to get that C of n is the way I showed you by taking derivatives. So the first derivative looks like this, and it's all impulses. And this is x prime e, correct, class? All right. Now once I have that, okay, now once I have that, I know that x prime of t is equal to a Fourier series as well because it's periodic. And it's C0 plus the summation from n equals minus infinity to infinity of Cn prime e to the jn omega naught t. And I also know that my C of n is simply C of n prime divided by jn omega naught because I just took a derivative of that. Do y'all follow me on this? This is just straight out of stuff we've done. So to get C of n prime, I say that's equal to 1 over t, the integral. Here, when I take my window of integration, I want to go from here to here. I'm literally going to go down, and I'm going to adjust this. I want to be, maybe that's not quite. What I want to do is only capture 2 of these, and I don't want to end or start at a transitional point. Y'all with me? So this, I mean, this is, if I'm talking about the derivative, I'll go from, say, minus t over 4 to t over 4. It doesn't really matter as long as this range is a full t. Now, this function I have to put inside the derivative, inside this integration, and that's really going to have a magnitude of a, and it would be delta of t minus delta of t minus capital T over 2. So I'm just mathematically stating what's over there for the period between 0 and t. You all follow me on that, class? Do you see that? I mean, are you okay with, I want to make absolutely sure everybody sees it. Do you? No?
No.
What don't you see?
Why is the top of on T over 4 on T over 2?
I'm sorry, where is here?
Yeah.
Well, remember, I can integrate this over, I can go from 0 to t, where I can go from minus t over to 2 to t over 2. It's got to be over a range of a period, right?
Yeah.
Whatever this value is, this should be 3/4. Sorry. You're right. This should be 3/4 t. Sorry. It's got to be over a range of a period. All right. Anyway, I'm sorry about that. You're right. So I have these two here. Do you all agree that this is mathematically? And then I have to multiply by e to the minus j n omega naught t dt. And the reason I got the derivatives in the first place is so I get delta functions, and I know I really don't integrate a delta function. I just look at it. This one turns on at 0, right? So I evaluate e to the minus jn omega naught 0 or 1, and I can see it's going to be simply 1 over t times a, and it's 1 minus, and then it's going to be e to the minus jn omega naught, and then this is going to be t over 2 here. Y'all follow me on that? Good? Can you see it from over there?
Yeah.
All right. Now, after that, I've got my C0. Now I'm going to get my C of n. And the only thing I'm going to do is take that and divide it by j n omega naught. So I take that and I have a over capital T, and then I have, divide that by j n omega naught. I might as well do a trick here that you already know. I'm going to take whatever that angle is and divide it by 2, right? And then I'm going to pull that out, a half angle out. So, I mean, you don't have to do this for this problem. E to the minus j n omega naught. And now it's going to be t over 4, right? And then I have e to the j n omega naught, capital T over 4, minus e to the plus j n omega naught, capital T over 4. Do y'all agree with that?
Shouldn't one of those be negative?
Down to the back, this should be negative, my bad. Yeah, a little more.
If that's like the backhand one is negative, then when you pull out a positive exponential.
Yeah, just multiply these two. Don't you just add exponentials, right? And that'd be e to the 0, which is 1, right?
Yeah.
That's what we want right here. And this one, we want when they multiply together, we want 1/2. So you break out and you got 2/4.
Yeah.
Now, at that point, what do I do with this? I mean, we could do a few things. I want you to just tell you that omega naught right there is really 2 pi over t, right? And it's capital T there. So you could put 2 pi and get rid of the t's, correct? And then divide it by 4, so it's pi over 2. Do you all agree with that? Then I can see, so it's n pi over 2. I can see that this is a, what, 2j sine, right? So I'm going to go ahead and break that down and say this is really going to be a over j n omega naught times e to the minus j n omega naught. Actually, what I'm going to do is, since that's 2 pi over t times t, it's 2 pi over 4 is pi over 2. And then I'll put down the 2j here, and I'll put down the sine, and now it's going to be n times, well, 2 pi n. No, I mean pi n, pardon me, pi n over 2, right? Do y'all agree with that? I'm just cleaning it up slowly. So I'm going to get rid of the j's. Good deal? And I forgot the t, the capital T, right? So I'm gonna get rid of the j's first. And now, right here, you see how I have omega naught? Omega naught is 2 pi over cap T, right? So times T is just gonna be 2 pi. I'll put that in. So that's gonna be 2 pi n down there, right? What was the magnitude, 5 volt?
Yes.
5? See the 2's going up? All right. And I basically got that. And that means that this is going to be 5 over 2 n pi, correct? Times that. Isn't that right?
Just by it, right?
Oh, I'm sorry, you're right, pi n. I'm sorry. And it's that, right? So that's my C of n. You can evaluate it, just you'll notice for this one, all right, n equals 1, the sine of pi over 2 is 1, right? N equals 2, the sine of pi is 0, right? N equals 3, the sine of 3/2 pi is -1, right? So really we've got a series of, it's really -1 to the n plus 1, I think, is the series, if you want to replace it. But you can leave it like that. That's perfectly fine. It's falling off as 1 over n. Now that's C of n in the double exponential series right here. But in the cosine series, right? In the cosine series, I would have my v naught, or v of t, whatever this, they call this thing, that source function there. I have it as x of t. I can leave it as x of t. For the cosine series, you have C0 plus the summation, right? And now it's going to be of n equals 1 to infinity of 2 times the magnitude of C of n. Remember when I showed you this? Now it's not a doubly infinite, it's a singly infinite. It goes from 1 to infinity. And then it's going to be times cosine of n omega naught t plus the phase angle of C of n. Y'all with me on that? Now he chose not to use a cosine series. What did he do? He wanted a sine series, so what do? Phase shift by 90, which way? We've got the C of n's. We could say, therefore, x of t is equal to C0 plus, does he ask for the phase or just the magnitude of coefficients?
Magnitude.
All right, because he had a sine series. So now it's still going to be 2, right, times magnitude of C of n. But now it's going to be sine of n omega naught t plus phase angle of C of n, whatever that is, plus what? Well, think about it. Sine of 90 is cosine of 0, right? You with me? Isn't really a cosine wave ahead by 90 degrees? Let me say this another way. Sometimes I get myself in trouble saying it. I know if I look graphically, this is a cosine wave, and this is a sine wave. I hope you can appreciate it. So I look at this is exactly 90 degrees, right? So if I take the value of the sine wave and subtract 90, if this is x, and I subtract 90 from it, I have the cosine wave, right? And if I have the cosine wave and I add 90, I have the sine. Does that make sense to everybody? So I'm just going to add 90 here, or plus pi over 2. And now this is the actual phase. All right, because he put it in the sine series, right?
Yeah, but I think that answers you solve forward in terms of cosine, because I was missing the factor 2.
No, 2 comes right here.
Right, but I did convert the cosine, and I was missing the factor 2, so I didn't know how.
Well, but for the magnitude, this is the only thing. You're talking about the angle you factor it to?
No, just the magnitude.
Well, the magnitude's right here. It doesn't change at all. All right? The thing is, for a single exponential series, you just have C of it. For a double exponential, when you have a cosine series, you only sum it from 1 to infinity. This becomes 2. You follow me on this, Jacob?
Mhm.
All right, so let's just do it. We'll get a few of them. For C0, our C0 is going to be 5/2, 2.5 is C. What did he want, though? Did he want the current? I forgot what he wanted.
There's a circuit.
Yeah, I know it's a parallel arc. Let me draw the circuit right here. This is a good problem, by the way. I could see, I mean, if you're going to work for somebody and they want to make sure, you know, when you say you've completed your degree, that you know what you're talking about when it comes to the circuit. I can see him giving you this problem just to see how good you are, or something similar. So here the circuit looks like this. You got your clock over here, right? And it's 0 to 5 volts, and it has some fundamental frequency and 50% duty cycle. And then you have a resist. Is that a current though?
Yes.
I'm sorry, this is a current I. And then he has a resistor in parallel with a inductor, right? Okay. I put this as X of T. I might as well just call it I of T. Now this is the source I of T right here. Now, I'm going to go through this. I want to make sure you all see this. They want the current through the resistor and inductor. Okay, well, if they want this current I right there, y'all know that this is in the phasor domain, call it IL. This would be the current entering the parallel sum, so it would be I right there. I of, really be N omega naught, right? And, sorry. This would be my I2, and I'm just going to put it of omega, would be equal to this one, my source value, I of omega, and then it's going to be times the opposite impedance R over the sum of the two, or R plus J omega L. Are you with me on this, class? Remember, if you want the current through an element, if you have the current through both elements, you take the opposite impedance and you add the sum of the two and multiply it by the current going through both. Do y'all remember this? All right, well, we don't have omega. What we really want is our transfer function. And the transfer function is the relationship to output to input. So our H of omega is really, the output is I of omega. I2 divided by my I of omega, and it's simply R over R plus J omega L, right? Y'all with me? Now, I gave you this, and I showed you when you modify this, right? You would put, also you would add one thing to it. If you wanted the output, you would add plus the phase angle of H of N omega naught, right? You're going to add that, and then you would, in here, you would multiply it by the magnitude of H of N omega naught. Do y'all remember that, class? I'll write it right here, nice and big. So now I can say my I of T through the inductor, this is in the time domain, which would be C0, and then I evaluate this as 0. Do you all see that this function when omega is 0 is just R over R is 1? So it's just C0, it's the average value of the current. Plus, then it's the summation from N equal 1 to infinity of 2 times the magnitude of C of N, and I erase C of N. 2 times magnitude, it's A times 5, I'm sorry, 5 over what, pi N, and this is just magnitude, and then there's an e to the minus j and pi over 2 in there, right? We're gonna throw this into the phase in a second. Is that the magnitude? Just tell me. Okay, leave that alone right there. Then it's the sine of n omega naught t plus, wherever I had it, the pi over 2 plus, and then it's going to be plus the phase angle of C of n. We'll get to that in 1 second. And then it's going to be plus the phase angle of this, right? Correct, class? So how do we get the phase angle of this? Well, this is really what? This is, if you want to, you can divide top and bottom by r, and you would have 1 over 1 plus j n omega naught, and then you would have L over R here, right? Correct, class?
Mm-hmm.
And the phase angle down here is what? The inverse tan of n omega naught L over R divided by 1, right? So the actual phase angle, the magnitude of this would be equal to 1 over the square root of 1 plus n omega naught L over R, whatever that is, squared. That's the magnitude. And the phase angle will be minus 10 to the minus 1 inverse tan of n omega naught L over R. Inverse tan, because down here, this, if you have this right here and you want the angle, this is the tangent. N omega naught L over R is on the vertical axis, 1 is on the horizontal. So opposite over adjacent is tan. Therefore, this downstairs would be plus tan, inverse tan of n omega naught L over R. Upstairs, you have to throw a minus sign, and I'll circle that. So these are the values of my h of n omega naught. And let me actually add that in here first. I'll put the magnitude of that. So it's 1 over square root of 1 plus n omega naught L over R squared. And then times the sine of n omega naught t plus pi over 2 plus the angle of C of n. And for C of n, help me out here, C of n was equal to 5 over n pi times e to the minus j, and here it was n pi over 2, right? And then it's times the sine of n pi over 2, correct? Isn't that right? Here's the deal. See, that can be negative. When you have minus 1, that's 1 at an angle of minus pi. Y'all follow me on that? This right here is pretty easy to follow. Just increment in. All right? So this phase angle here, if you look at it, is, well, what could we do with that? We could fuss with this some more, but this phase angle is just going to be minus n pi over 2. I can put that in there if I want. All right, and then this phase angle, you have to take a look at when n is equal to 0, it doesn't count. N equal 1, this is 90 degrees, right? N is equal to 2, well, you can actually do it that way. You can do it that way. That's going to be, yeah, it's kind of strange because they're going to cancel. So this cancels that, and the phase angle is pi over 2. So out of curiosity, that's basically the whole 9 yards. Let's calculate a few of these values. I'm kind of curious about this myself. This is a good problem because it brings together a lot of concepts. And I may ask you to plot versus time domain this function using MATLAB or Octave, and I'll help you with it a little. But it'll give you some more, it'll really showcase this. So he asked the value of C0. All right, well, just look at this. We know it's just going to be the output is just going to be C0, isn't it? Which is 5 halves. Is that right? For C? All right, now, did they ask for 1?
1 through 7.
All right, for 1, I've got to look at this. So when I take a look for n equal 1, right, the magnitude is going to be, I'm just going down here, 2 times 5 is 10 over pi, right? That's this part. Then over here I have 1 over the square root of 1. Now, here the L over R becomes important. What is L over R? Just tell me. Is it 2?
Yeah.
Oh, that's beautiful. That's great. So it's 1 plus, and here it would be 2, and omega naught is 2 pi over t. And what is t?
1.
T is 2.
Is it 2?
T is 2.
Yeah.
So it's 2 pi over 2, or just pi, right? And then it's squared, correct? Gotta take the square root. So this should be the magnitude of the first one, if you can tell me what that is. I'm looking at that, about 1 there? I can't tell for sure. What do you guys,
I think it's 0.5.
10 over pi? Ten over pi is about 3, and that's divided by, what'd you get?
That's 0.5, that's what it says on here.
0.5? Is that what you said? Oh, I'm sorry, I didn't hear you right. All right, now the phase, if it says 0.5, I'm glad we got it right. Yeah, the phase angle should be 90 degrees, is that right? What does he have?
Negative 80.96.
All right. Help me here for a second. If, and tell me if I'm crazy here, n equals 1, oh, that's minus 80? You know what? Because of the phase angle that I didn't put down correctly here, this is the inverse tan. Somehow didn't put here. It should be plus or minus the inverse tan, right? Of n omega naught times L over R. Remember that inverse tan thing for the angle of the H? We forgot that one. So it's, what is that angle going to be? If you find this angle, so it's at here. The angle will be 90 degrees minus, and this, well, actually pi over 2, my bad, pi over 2 minus, and then the inverse tan.
Where are you,
Uh-huh.
I was just asking, where are you sticking that negative for the tan?
The angle has to go right here. See this?
Yeah.
I forgot to put it right here.
That's part of that H, or that is the H?
This has to be the angle associated with the transfer function.
Yeah.
So the transfer function we had here, I erased it, but you remember it had R over R plus J omega L? And then I divided by R, so I had 1. So I need that angle, and it has to go in there, and that's what that is, right? And this is n omega naught, which is 2 pi over 2, or pi, right? And then L over R is 2 as well, isn't it?
L over R is, yes.
So it's 2 pi n. That almost looks like an angle, but it isn't. And I can't tell what that is. So what is the inverse tan of 2 pi n? In radians? You can do it in degrees. You put it in degrees and then subtract that from 90.
Well, I got 9.
Just give me this in angle, just the inverse tan of 2 pi times 1. inverse tan,
Z,
what's that?
819 is what I got.
After you subtract it from pi, what,
That's what I got.
for this?
Yeah. Oh, I'm stupid.
Oh,
I'm in degrees.
hold it, no, that's right, because these two cancel. That should be just this phasing, I'm sorry. This, the 90 degrees cancels the 90 we added. But what do you get for this again? Because the C of N has a phase angle of just
It's
90.
8.1, well, it's 8.9, but it's supposed to be negative, so I'm confused.
No, there is a negative sign right here.
Oh, it's, okay, then, yes, I got 8.9.
Yeah, that's how you get it. The phase is not that important. The magnitude is. So what, but you can go through and sequentially go through the other values of N. It'll come out right, all right? The real thing is the magnitude, though, they worry about, not so much the phase. Because they always want, if you get a magnitude above a threshold, an FCC threshold, an EMC, your product doesn't pass. The phaser could care less about it. And that's the real thing. All right, other questions about the homework? Sorry it took so long on this one, but it really,
I appreciate that.
it goes after all aspects of the EMC. I'll tell you too, this whole thing with just, oh, that's the bandwidth of that waveform is this. So we don't have to worry about frequencies beyond that is generally a very dangerous assumption. Because you can get yourself killed with FCC laws, assuming that. Bandwidth can be anything you want. It's what the actual harmonic size is or what the values are at higher frequencies. What else?
3.2.5.
Okay. From a book. Okay. Okay, first we need to draw this thing. I don't think he has a picture in his book. Or maybe he does. This is really just understanding how to get the frequency domain signature of the input and then taking a look at the output circuit to see how it's going to be affected. Okay, so they tell us that they have a trapezoidal waveform like this that's repeating, right? Magnitude A here is what? 5 volts?
Yes.
And the rise time here is what?
2 nanoseconds.
10?
2.
All right, that's fast. And what is tau, non-time, or the duty cycle, either one? Duty cycle is 50%. So tau over T equals 1/2. And what's the fundamental frequency?
10 megahertz.
Pardon me?
10 megahertz.
All right, so it's 10 to the 7th hertz. It means T is equal to 1 over F naught, right? Or 10 to the minus 7. And that makes tau equal to 5 times 10 to the minus 8 seconds, or 50 nanoseconds, right? Go through it all. Now, after that, I go ahead and I put, the first thing is going to be 1 over pi tau is going to be the first frequency I worry about, and then it's 1 over pi tau rise. Can you tell me what this one is? Y'all know what I'm doing, don't you?
Yeah, 6.4 times 10 is 6.
I think it's 6.36 times 10 to the 6 hertz. So 6.36 megahertz, and down here, this one,
15.9.
15.9.
Yes, sir.
All right, I'm gonna put this as 6.36 megahertz. And this is 15.9 megahertz. Okay. And the fundamental is 10 to the 7th of 10 megahertz. Is that right?
Is that?
Yeah, fundamental is 10 megahertz. You're trying to find you're trying to find the capacitive value that would cause a 10 dB drop on the fifth harmonic.
Yeah, well, first you gotta,
Right, so you need the fifth harmonic.
wait a second, just the capacitive value?
Well, there's two parts. That's the capacity value, then you're trying to find.
What's that?
It's that you're trying to find the capacity value first.
And the second part, you try to find it when they give you a certain value.
All right, for, help me out here, what does it give you? It gives you an internal voltage.
Yeah, it's 10 volts.
Internal resistance.
No, it does this. It's saying that this is the clock, right? This is an ideal voltage, right? And then it's got an internal resistance here,
10 ohms.
10 ohms. And what is it feeding?
There's one capacitor.
What?
There's one capacitor in series.
Here. And back, that's it?
It says oscillator, but I don't know.
What's that?
It looked, maybe I'm thinking about the wrong problem. Is that the one where it says?
Yeah, well, it says it feeds like a capacitive
It has a-
value in the oscillator output.
Let's see, it's right.
Hold on. Okay. So here's the deal. We know at the fifth harmonic, doesn't matter what frequency is. Whatever this value is, this value is. Right? That's it. If we want it reduced by how many dB? 10 dB. So they're saying, find me a capacitor. They don't know what this is. So it's down by 10 dB. First question is, how much is that going to be down? Right? I mean, if it's no longer going to be V naught, so what is the value? Well, here's the thing. The transfer function for this thing, all right, I mean, they want this to be down by 10 dB, correct? So we need the transfer function of this. Well, this has an impedance of 1 over Jn omega naught. You all agree with that? Mm-hmm. So if I look at V out here, this is kind of a tricky problem. You got to read through some stuff. If I look at this here, and this is my V out, I can say that V out over, and I better call this V source over V source, that is my transfer function, right? And that's equal to this impedance. Well, actually, let me do it this way. No, I'll do it this way. Jn omega naught C over, and then it's going to be that impedance plus R, or plus 10. Y'all agree with that? Now, what I'm going to do is multiply top and bottom by Jn omega naught C. And when I do this, I have my H of n omega naught equal to 1 over 1 plus Jn omega naught C times 10. Agreed? Now, when I take a look at this, right here, I can say the magnitude of that is equal to 1 over the square root of 1 plus n omega naught C times 10, or 10C if you want, 10C squared agreed? So we want this thing to be minus 10 dB. Obviously, the transfer function was 1 when there's no capacitor, or C is 0, correct, class? If C is 0, just look at that, it's 1, right? That's 0 dB. We want it down by 10 dB. So we want minus 10 dB. It says minus 10 dB, right?
Reduce, yes.
So that's going to be equal to 20 times the log, right, of the magnitude of that. Do y'all follow me? Magnitude of that is what? 1 over the square root of 1 plus n omega naught times 10C squared. I'm going to make this simple. I have 20 log of 1 minus 20 log of the second. Do y'all agree with that? 20 times the log of 1 is 0, so I'm just going to put minus 10 here is equal to 20 minus 20 times the log of 1 plus n omega naught times 10C squared to the 1/2 power. Do you agree with that?
Mm-hmm.
The square root is really 1/2 power. Good with it, Jacob?
How did you go?
I broke this up into log of 1 minus the log of the bottom. Log of 1 is 0. All right, now I'm going to just do a few things here, but just pay attention for 1 second. We'll be done with this. Y'all see how the 1/2 can come out front? So, right, if you have, just so everybody knows this, if you have log of x to the a, or n, maybe better, that's the same thing as n log of x. Do you all agree with that? Some people, believe it or not, especially on a Friday, you get a little fuzzy about certain things. So when I take the 1/2 in front, this becomes 10. Agreed?
Mm-hmm.
And now I just divide by minus 10. And I get 1, right? And now I take both sides to the 10th power. So this becomes 10 is equal to 1 plus n omega naught times 10C squared. Agreed?
Mm-hmm.
Jacob? Did you ask me this, or Jacob? You all with me?
Mm-hmm.
I'm going to subtract 1 from both sides. Doesn't matter how you proceed at this point. I'll take the square root of both sides, 3 on this side. And what harmonic? What frequency? Or what harmonic?
Negative. Oh, what?
Fifth harmonic.
Fifth harmonic in the fundamentals, 10 megahertz. All right, so then you divide this by 5 times 2 pi, right? Times 10 to the 7th and then times 10 to get C. Right?
Mhm.
And that should be the value of C. And I don't know what that is, but that's how you get it.
I should give some 955.
I think it was 900 something.
Is that what that is? Confirm? Like, that's how you do that part. Now, what's the next part?
Given that the open circuit voltage transition from 0 to 5 volts, estimate the level of this fifth harmonic.
It's just saying, I want you to calculate at the fifth harmonic.
They want the output of the fifth harmonic with this. All right. Now, this is basically what we did before. The only thing we're going to do is we've got this, right? We got to find the fifth harmonic. So the fundamental is 10 megahertz.
Yes.
The fifth would be 50 megahertz. That's way up here. I'm just going to talk. If you want me to, I'll do the whole thing, but follow me on this. Y'all understand how to find this level out here?
Mhm.
Once you have that, that's your input voltage. And then evaluate the circuit's impedance at the fifth harmonic, and you can do it. Did you want me to do it? I'll do it, but it's a very straightforward thing. Do you understand what I'm doing? No, not you. Not you, Jake. Right. I mean, do you? I want to make sure. Yeah. Okay. Then I won't do it, but it's straightforward. But you got to get that transfer function right. Other questions? The looks on a Friday afternoon, I wish I had a camera out there. So, what's crazy, I love it with you. I mean, I've got the quiz and I'll give it to you, so get out of here. Where I'm going with this, the next stuff we're starting, we're actually a little ahead of schedule. Amazing, I'm shocked. We're going to the microwave. We're basically done with that chapter. And, I mean, you can take a look at it, right? Or I'm going to do the common mode choke stuff
From the book.
in the book. If you take a look at your book, I'm going to do the common mode choke. But I'll level with you. As far as EMC, we've looked at the elements. The only thing I'm going to do is common mode choke. I just mentioned ferrite beads, but that stuff's very easy to do. We've gone through digital signals. Now, filters, I'll level with you. Most of you know what low pass, high pass, band pass filters are. The only thing I'm going to do is it's called a common mode choke. It's a ferrite choke, and I'll do that on Monday. And then we're jumping into chapter 10, microwave engineering. And this is really interesting stuff and very useful stuff in this day with nature. But I'm going to, now, any questions before we got on into the quiz? I wanted to tell you, I've been a professor, I've been a faculty member down here since the fall of 1985. And I've seen all sorts of things in classes, huge classes, small classes, COVID classes. I've seen just about everything you can imagine. And one of the things that I try to do is assess a class overall based on how they perform relative to a prior class. This is a good class. I get questions. It's a summer class. Usually people are more relaxed. A lot of times, a lot of the kids I have in summer classes, at least for the ENAM 1 stuff, they flunked the course one time and they're taking it again. So they're not usually the strongest students, but this class is good. And I get a lot of questions. And I get a lot of interest, despite a Friday afternoon class, an afternoon class in general, after lunch, heat of the day, not the sharpest. I mean, it's usually people are not that pep. Usually the 9 through 11 o'clock classes are the best.
It's easier to talk with less people because it's more personal.
I can say things around here. I don't have to worry about somebody going to the